Hi everybody, thank you for joining Quantum Detectors today. I'm Chloe, the Marketing Manager. We're kindly joined by Matt Wilson, the Group Leader for Detector Development in STFC's Technology Department. Matt will be giving an in-depth introduction to HEXITEC. If you have any questions throughout, please feel free to use the chat log, and I'll pass over to you, Matt.
Lovely, thanks Chloe. So hi everyone, I'm Matt Wilson. So today I'll be talking about HEXITEC, which is a fully spectroscopic hard X-ray imaging detector. Just to start with the disclaimers. So I work for STFC, which is part of UKRI. So I'm not part of Quantum Detectors, but we're on the same campus, which you can see behind me, and we work closely together. I'm part of the team that's developed HEXITEC over the last 10 years. And this work I'm presenting is all down to them as well, and all the collaborators that have used HEXITEC as well. So it's all our work I'm presenting. HEXITEC's now sold by Quantum Detectors, and really the motivation for me and STFC, but also Quantum Detectors, is we want to see as many people as possible using HEXITEC. So the purpose of this talk is to try and give people a bit more insight into the technology, hopefully show you what it can do and where it can be useful for you, and then that can help us then start to get more users, grow a bit more of a collaboration and user community where we can all help each other to make the most out of the technology. So there's just a spec sheet there, which is available on the Quantum Detectors website and the specification, and we'll go through this as I go through the slides today. So today I'll tell you where HEXITEC has come from, so its background and motivation, explain how it works and what that means in terms of handling data and some potential pitfalls that come with the design of the detector. Show you some example applications which have come from our collaborators from around the world, and just see where we are heading and what we can do in the future as well. So just to give you a little bit of background, so HEXITEC was first developed by STFC as part of a basic technology grant that was led by Manchester, and it also had University of Surrey, Birkbeck and Durham University involved as well. It's funded by EPSRC. In fact, that grant is what generated the job that I first got with STFC. So it goes a long way back from 2006 when it first started. After that grant, we had a second one within STFC, which is to try and develop and translate the technology a bit more. So we had some partners on board from a hospital in Surrey and also UCL looking at some different applications. It's probably not until that point where we really understood where HEXITEC can be used and what its unique selling points were. So following on from that, we had lots of developments in-house to try and improve the technology and work with lots of different people to try and find different applications, make sure it works for them. And then eventually we started to get more and more users. So these are sort of a list of our friendly users from STFC. Many of people are probably on the call, but also people that I've stolen their work to present on this as well. So this is my coverall thank you to everybody as well for all the work that we've done over the years. And then 2 or 3 years ago, the technology was licensed to Quantum Detectors, and they've then gone on and made improvements on that technology again. It sort of made it more customizable for customers as well, improving the usability. So the things that we don't do very well as scientists, but they do very well in industry. So HEXITEC, what's it all about? So the idea behind it was that we wanted to try and measure the energy and position of every hard X-ray. So this is in the energy range from about 10 kV up to 150 kV was the spec. And to do that, we use a semiconductor material. So this is typically cadmium telluride, and this is my very basic cartoon of the cadmium telluride block here. We've got the pixels on the bottom, and then the planar contact on the top. We connect electronics to each of the pixels, and then we have a very simple way of trying to measure the voltage on those pixels. We apply a bias across the detector. So this is typically 500 volts for a 1 millimeter thick cadmium telluride detector, which generates this electric field. And then when an X-ray comes in, it generates electron and hole pairs. So for every 4.4 EV of the X-ray, we get 1 electron hole pair. So a 44 kV photon is going to give us 10,000 electron hole pairs in a charge cloud. And that charge cloud then drifts under the electric field. And as it drifts, it diffuses and expands due to electrostatic repulsion. Then when it gets close to the pixel, it induces a signal on that pixel. And that signal is induced due to the small pixel effect or the Shockley-Rameau theorem. and that gives us this voltage pulse on our electronics. That voltage pulse is proportional to the charge which was deposited by the X-ray, and in turn that gives us the energy of the X-ray. So the whole purpose of HEXITEC was to try and measure that voltage, that energy as accurately as we can, so that we can then do spectroscopy on the images we're taking at the same time. So the way we do that in HEXITEC is that we actually try and have a very simple pixel electronics. So we want to keep the ASIC operating in a very synchronous way. There's no asynchronous clocks, there's no resets or minimal resets going on. So we're not getting lots of different crosstalk between the pixels, which introduces noise. So what we have is that we have a bond pad, which connects the electronics to the detector material. Then we have a charge amplifier with a feedback circuit. And when we get this voltage pulse that comes in, we get this black signal here. So we get a rise time of about 50 nanoseconds. And then this feedback circuit is then slowly putting current back into the amplifier to restore it back to baseline. And then this happens over the next sort of 100 nanoseconds or so. To get a clean signal, we want to shape and filter that pulse, and we use that with a second order pass filter here. And this is just a standard RC/CR shaper, and this has a peaking time of about 2 microseconds. So that tracks the output of the amplifier and gives us this nice smooth rising edge and this blue trace here, and that's connected to a peak hold. And the peak hold tracks that level and gives us stores this voltage level. So that's giving us that measurement of the voltage, which gives us the charge, which gives us the energy. It's also worth noting, we'll come back to discuss this later as well, is that recovery, the preamplifier, is also then seen in the recovery of the shaper. And that's another slow process, which becomes a factor in how we consider how we operate the detector later on. The other thing worth noting is that the energy range that we actually achieve is about 3 to 180 keV per pixel. And there is, for those who've got the eagle eyes, a switch in here, so you can change the gain of the amplifier. That would go to a lower gain, so we go out to around 600 keV per pixel. And that isn't something that we typically use because we're limited in the detector material efficiency. But if it is something that you're interested in that high energy range, that's worth speaking to quantum detectors about, I know they might be able to accommodate that as well. So that pixel electronics is repeated 6,400 times in the ASIC itself. So there's an array of 80 by 80 pixels on a 250 micron pitch. And that's what this array is showing along here. I'll just turn off the laser pointer so it doesn't crash. We have wire bonds along the bottom edge, which gives us our three-side buttability of the device. And the output of the chip is along 4 different outputs. So we have 4 blocks of 20 by 80, which I'll explain a little bit more about later. And we use a rolling readout system. So we measure out each row in turn, which means we're continually reading out all the values from the chip. And we have a dead time of about 200 nanoseconds per row for each frame. We operate with a 21.25 megahertz clock, and the maximum frame rate that you could do if you rattled through all the pixels as fast as you can would be about 9 kilohertz, but we typically operate about 5 kilohertz for stability and software reasons. So how the readout works, so we've got the chip here, we've got our registers along the edges. So these are the things that tell us how to set the pointers and how to read out the pixels. We've got the pixel array across the middle here, which is our 80 by 80 pixels. We read out the detector in 4 blocks of 80 by 20 pixels. And what we do is we select the row, which is what this green line is here, selecting the first row. We sample the peak hold in that row. We reset the peak hold, and then we read those values out as analog voltages. We then immediately go to the next row. We sample the peak hold in that row and reset it, and we read it out again. And then we just repeat this process going around the different rows over and over again. And that's what we call a rolling shutter readout. So at any one time, we'll be reading out a row, and then the rest of the rows will be active in that time. So there isn't a global shutter where all the pixels are active and then they're all being reset. It's a constant rolling shutter. Okay. That ASIC is connected to the cadmium telluride material I mentioned earlier. So we typically use 1 millimeter thick pad tell for macro rad. So this is something that we've done over many hundred detectors now, STFC and QD between us. What we have is an array of 80 by 80 pixels with a matching 250 micron pitch. We typically have a 50 micron gap in between pixels. And we use this material because it's got a high atomic number and a relatively high density. So that just means it's got lots of electrons, and those electrons are going to stop the X-rays when they're interacting with the material. You can see at the bottom there, compared to silicon, it's got a much higher stopping power. So at 100 keV, it's stopping around 65% of the photons incident on it. It operates at room temperature as well. So we always operate HEXITEC at room temperature. And the acrored material, the pixels that you can see there look gold, but underneath the gold, there's aluminium. And that aluminium gives us a blocking contact or a shocky contact with the CAD cell itself. And this is a blessing in disguise. So in some ways, it's really useful because it's blocking the charge or the dark current generated from the CAD cell. And that means that we can have low noise electronics and we get the good spectral performance. The downside of that is that charge can't escape the detector. And that over time, that can build up and start to cause a phenomenon which is called polarization. It's very easily solved, but it means that we have to do a bias refresh or a charge flush to get rid of that charge at different periods of time. So here's an image of HEXITEC, so some data coming out of HEXITEC from an americium sealed source. It's not a flat field, which is why it doesn't look so uniform, but it's operating at 28 degrees C and 500 volts. And what you can see is 1 minute intervals taken at 5 minute gaps over a half an hour period. And the CAD cell itself will always have some kind of defect levels in it. It's not as sort of a purer crystal as you'd get from silicon. So there are always some inherent defects in the material itself. And you can barely see them in the first minutes, but there's some hints of some non-uniformity there. And those non-uniformities are areas where there's crystal defects, and that's generating high leakage current in that particular area. So it's these areas of high leakage currents where that charge won't be able to escape the detector and starts to build up and deform the electric field and start to affect our charge collection efficiency. So you can see after half an hour, we're starting to get more noise events at the bottom of the spectrum. So down here at the spectrum, we're starting to lose events and start to get more noise. We're starting to lose some events here where the electric field isn't giving us full charge collection. But that's very easily recovered. So all we have to do to stop this happening is turn the bias off the detector for about 1 second. And this is just what we call a charge flush, and it happens automatically in the software. It's something that's taken care of for the user, but just something to be aware of. You can operate the detector a little colder, and that slows down the amount of leakage current generated, which slows down the polarization effect. So there is some customization that we can do around this to sort of optimize it for different applications as well. So again, that's something to speak to quantum detectors about if you have any particular needs about how much, what collection times you need to have and continuous operation. How we stick the ASIC here to the CZC is with a process with gold studs and silver epoxy. So you can see here in this electron microscope image that you've got the studs on the ASICs. These are made from a gold wire, which is typically around 20 microns in diameter. But when the ultrasonic force is applied to the pad on the ASIC, it gives a diameter of about 50 microns at the base. And it comes up into a peak, which is about 30 to 40 microns tall. And then on the cadmium telluride, we have a screen printing technology where we screen print silver-loaded epoxy onto the pixels, and you can see some of these little lumps of silver epoxy, which when you look up close, look like little flakes, which have got a diameter of around 10 to 20 microns each, and they pile up to give us a diameter of a bump, which is 100 to 120 microns, and typically 40 microns tall. And it's worth noting that with this material, we don't actually see any of the X-ray fluorescence from the gold or the silver, because they're behind the cadmium telluride itself. So they're underneath the cadmium telluride, so we don't see any effects from this. And the cadmium telluride also acts as a radiation shield for the ASIC itself. So we get the benefit of the stopping power of the material, one in its detection, but also it acts as a shield automatically for the electronics as well. So when we have these two devices, we've got the gold studs on the ASIC on the top, and then we've got the cartoon of the silver epoxy on the detector. We press these together in a flip chip machine. We apply pressure on the top to get that insertion. We heat it in situ, keeping it at a relatively low temperature because the cadmium telluride is quite sensitive to temperature. So we need to keep that below 120 or 150 degrees C. Once that's cured, we take it out of the machine, we flip it over, and then we connect our base plate to it, so an aluminium base plate, and then there's a readout PCB we're connected on the bottom. We wire bond to the ASIC, and we apply a wire bond to the top to apply the bias to the top of the detector, so at 500 volts, which gives us the electric field. And then it gives us our finished module, and then that plugs into our readout electronics. So it's a modular design that you can put into the electronics, and you can swap them in and out even if you wanted to. And you can also see that it's a three-side butterball design as well. So the system that plugs into is the HEXITEC readout. So readout system itself has got a block diagram here. So we've got the HEXITEC ASIC here. The 4 outputs that we had from the peak hold are coming out as analog voltages. They come out as single-ended voltage levels with a swing of about 1 volt. And then they are buffered by an amplifier and turned into differential signals. We need the differential signals then to go into the digitizer. So we have a 14-bit ADC, and then that goes directly into an FPGA, which is on the board next to the detector. That FPGA is taking those peak hold voltages, so that energy per pixel value, and doing a dark correction per pixel. And that's done automatically in the FPGA, as is measuring the offset values per pixel as well. So it takes an average of 8,000 dark frames and stores them locally on the FPGA, and they're subtracted as the data is read out. And it comes out on a GigE module here. So it's just a standard GigE protocol. So it just plugs into your PC or your laptop, and it's ready to go. And likewise, it's just a 12-volt input from mains with a 12-volt adapter. Within the DAQ as well, the FPGA acts as a state machine. So that's generating the clocks, which is causing this rolling readout that we saw earlier, and pushing and dictating the timing of the ASIC. And it's also doing some housekeeping as well. So there's some measurements of the temperature and humidity inside the box. It's also generating the high voltage and controlling that and doing that charge flush automatically with that 500 volt supply to the CAD cell. And there's also a PID controller, which just keeps the ASIC and the detector at a constant temperature. So it isn't doing very much in terms of cooling. It's just trying to keep a stable temperature and keeping a stable supply and level for the ASIC. So this is what the system looks like now. So the first thing that you'd notice if you've seen the previous systems that have been designed by scientists is that it's colorful and it's got some nice curved corners on it. So it's gone away from the designs of a scientist to something a bit more attractive. So I'd also say as well, it's a lot more robust than the things that we've designed as scientists in-house in STFC. So it's a much more useful product that can be sent around the world a bit more easily. It's a plug and play system essentially. So you've got the 12-volt adapter in here, and then you can have an Ethernet connector here, which can be up to 10 meters long quite easily. And then your X-rays come in through the top here. This is just a protective cover on the top, and the size of the box is about 25 centimeters by 8 by 7 centimeters. And there's a few mounting points around it as well. So this is a system that's ready to go. There's systems available in quantum detectors as well. So hopefully it's a relatively easy system for people to pick up and take demos from. Even with COVID restrictions, it can be sent around and used quite easily. What it outputs is essentially raw frames of data. So what you get from it is all of these rows of data that read out continuously. They all come out of the detector and they go into the software. So if you saw the raw data, you're getting these continuous frames of data where you've got all of the 0 values as well as the X-ray events. You can see the X-ray events there. We'll go through them a little bit later on. So the frames are 80 by 80 pixels, which matches the size of the array. Some rules of thumb are that the raw data gives an output of about 2000 ADU, which is equivalent to 60 keV, which is always a useful number to remember. The low energy threshold we typically operate at is about 50 ADU, which is equivalent to 3 keV. And that raw data can be used then to generate calibration coefficients, which would come with the detector. And we'll go into that in a bit more detail later. The software that you receive from quantum detectors, if you've used the STFC software, you'll notice it's a lot simpler. It's also more stable and faster to use as well. So it's straight out of the box. It should be a lot easier to get started and use. You've just got a single page, which you can see here, which gives you the ability to save the raw data or the process data, and then also view back the process data on the fly. So as you're capturing the data, you can see what you're getting. It's a Windows software with a minimum requirement that comes from the spec sheet. It should be something that's standard for most people to have. It'd just be a simple laptop. But any problems with the computing as well, that's something that you can talk to quantum detectors about. Also in the software, there's some very simple buttons. So you don't need to know all of the information about the detector itself. There is basically a collect and stop button on there. So you can set how big a file size you want to collect in terms of size or in terms of time. And then you can collect it. And then on the bottom in the orange box, you can see you get some feedback about what's going on. And then the images that you can see is that you've got a spectrum. So that raw data has been converted into an energy spectrum per pixel and a total spectrum from all the pixels. And then you've got some sliders here, which allow you to define an energy window, which means then you get an image for a particular energy range of interest. So it's a very simple and user-friendly software that you can get to grips with quite easily. The performance that we get is we typically have, you can see on the top here, a little pointer moving around and showing the spectrum per pixel for a detector. We typically have 1 kV full width maximum per pixel at 60 kV. So we use an americium source, which is the spectrum you can see there. And we use that 60 kV peak as our figure of merit. As I mentioned before, the cadmium telluride itself inherently has some crystal defects. We can't get away from that, but they don't have a very big impact at all. So on the edge of pixels where we have slightly more leakage current or any less ideal pixels, then we might get slightly more leakage current and more noise. But typically these will be a very small percentage. So you can see here in this distribution, there's a very small tail above 1 kV, but typically we'll get nearly all the pixels less than 1.5 kV full width half maximum. And then to go on to look in a little bit more detail at the data. To understand the data that we're getting, is probably worth just going over what type of events we get. So I'm stealing a little bit of the information from a paper from Leicester, who've done some excellent simulations about the detectors to explain the observations that we see from HEXITEC. So as we saw before, the charge clouds diffuse and have an electrostatic repulsion as they drift through the detector. That gives them a finite size, and the full width at 10th maximum is about 65 microns in cadmium telluride. So it's getting comparable to the pixel size. So when we have this interaction in the middle of events, we'll see all of that charge being collected on a single pixel, and we'll measure that whole energy on that pixel. So that's a nice, simple 1 pixel event. We can also have events occurring and landing in between pixels. In this case, we call this charge sharing. So some of the charge will go to one neighbor and the rest of the charge should go to the other neighboring pixel. But we can have charge loss in the interpixel region, or we can lose charge because the amount of charge sharing is less than the threshold of 3 kV that we have from the electronics. So there is an ability to lose some of the charge when we have this charge sharing effect. We can also have charge sharing where it's not just down to where the location where the X-ray interacted, because once you get above the K edge of cadmium tellurium, the detector itself will fluoresce. And that means that a single photon can interact in 1 pixel, it will fluoresce, and that fluorescence X-ray will be detected in a neighboring pixel or even further away from a neighboring pixel. The mean free path of the cadmium tellurium fluorescence is around 100 microns. So typically, we wouldn't be able to tell the difference between conventional charge sharing and charge sharing with X-ray fluorescence if we couldn't see the energy. But these X-ray fluorescent events can also actually escape the detector or move further away. So this can cause some artifacts in the spectrum that we need to be aware of and be able to account for. As you get to higher energy, you get the same effect from Compton scattering as well. But typically, that's above 100 kV and most applications would not be operating there. So in a single frame, we get lots of different events. So if we look there, we've got charge sharing between 2 pixels, single pixel events, and we've got these funny L shapes and squares as well. So when we get the raw data, we're trying to look at all these different events, work out what's happening there and trying to correct that data. I'll show you how we do that later. But it's important to remember that to be able to do that, we need to have gaps in between the pixels. So if you have too many events, then that means that you won't be able to tell if you've got charge sharing or separate photons happening in neighboring pixels. So we typically want to operate the detector with less than 10% frame occupancy. So that means with around 600 events per frame. When we do the charge sharing, the easiest one is to do charge sharing discrimination. So this gives the best spectroscopy, but it means that we have to throw away maybe 30–40% of our events, depending on the energy range we're using. It depends on the application whether this is a problem or not. So what the charge sharing correction is doing here is removing those events. So the charge sharing events, which you see in the light gray, are all giving us continuum in the spectrum here. And we also still have these peaks from the cadmium, tellurium, as well as the neptunium peaks here. And what we do by throwing away those events is basically get rid of that continuum, and we get these nice sharp peaks coming up from the zero baseline up to the peaks there. So if you want the best spectroscopy and you're not too worried about your efficiency, then that would be the correction to use. For charge sharing addition, here we've got an example of a frame of data. We've got many events here which are shared between pixels. And what we're doing in the charge sharing addition is that we're looking at the neighboring pixels and assigning a shared event, assigning the sum of the shared event to the pixel with the highest fraction, and gives us this frame output here. This is a different paper from Leicester. Well, Sarah is now also at Loughborough as well, I should mention. But essentially, there's a problem here in that we've got some charge loss in the interpixel region. So if you're looking for spectroscopy and efficiency, and when you do charge sharing addition, you can be left with this low energy shoulder here on the peak. So what's happening here, we've got the pink spectrum, which is the raw data with the charge sharing continuum again. In black, with the low baseline, that's the charge sharing discrimination. And then when we add in the charge sharing addition, you can see with the red, green, and blue, as we add in more pixels, we're getting a higher fraction of this low energy shoulder. And that's because we're missing some of the charge, because it's going in that interpixel region. What we can do to correct for that effect is to look at the ratio between the two charge sharing events. So there's been a lot of work done by Leicester, Palermo, and Illinois looking at these effects. And essentially you're comparing the energy on the two charge sharing pixels, and at 60 keV, the ratio of the charge sharing should mean that this line should be where all the events fall at, but what's actually happening is there's some charge loss here. So this yellow line in here is showing you that when you look at 30 keV, you should get 30 keV in the neighboring pixel, but you get more like 25. So there's some charge loss going on there in that interpixel region. What's also noticeable is that the X-ray fluorescence, so those events that can travel 100 microns in the material, they're not having charge loss. They're not interacting in that interpixel region, and we are getting those events. So we need to discount them in the analysis. So if we look at the ratio between the charge sharing events, so the energy on pixel 1 and pixel 2 over the total energy, then we get this factor R. And if we plot that ratio against the sum of the energies, then we get this plot here. These green events are the X-ray fluorescence energies, and then we can fit to this plot here, and that's giving us a measure of how much charge is lost depending on the ratio of the charge sharing between two neighboring pixels. And that gives us this energy correction factor. So you can see that for where there is no charge sharing, basically we have these values of 1, so there's no correcting value. And then as the charge sharing becomes more equal, so in the middle where we've got 50% on each pixel, then we're getting a charge loss of around 5 keV, which matches up with that low energy shoulder that we saw before. And we can use this correction to be able to add back that missing energy in the data. So here we've got a charge sharing correction, charge sharing addition corrected spectrum in orange. And then when we add that correction factor in, this tail is reduced and those values are corrected backwards in the peak. So this gives us a boost in peak height and recovers the spectral resolution of the detector as well. It's also worth noting some of the spectral features in the spectrum. So when you have an exposure, you're going to get quite a few different lines, which might take some explaining. So again, from a paper from Leicester, in this case for a cobalt 57 source, here you've got a 122 peak, but then in there you also have the characteristic lines from cadmium to tellurium, which are here. So you're measuring the 23 and 27 kV peaks from the detector itself. They're actually coming from the main peak, so you also end up with some escape peaks here. So whenever you have a large peak above 30 kV, at 23 and 27 kV below that peak, you'll end up with some escape peaks from the cadmium tellurium itself. You can also get other different lines in your spectra as well, which are often hard to explain. But in this case, these are some lead lines which come from the shielding around the source and the shielding around the detector in this case. So when you get these raw spectra, it can often take some explaining to understand what's going on in there. That's just some tips of things to look out for if you've got some unexpected lines in the spectra. And it's also worth noting that the material can be light sensitive as well, depending on the wavelength and the intensity of it as well. So keeping the detector in the dark is always a good tip. We discussed before about the shaper having a finite size, a finite tailing on it and a rise time, and that we've got this rolling shutter. Because these pulses are relatively long, then there is a chance that we can read them out as the events are still rising or falling. So we also can apply an end of frame correction on the data to make sure we don't get any false events. So because we've got this rolling readout and X-rays are coming in asynchronously to the detector readout, it means we can actually sample the peak hold and read it out before the signal is fully formed. So this is the case here. We've got the readout on the rising edge of the shaper. So in frame N, we'll read out this rising edge. But in the second frame, so frame N+1, well, actually the shaper will continue to rise because it isn't reset, and it will read out the correct value. We can also end up reading out the tail of an event, which means in frame N, we read out the true value, but in frame N+1, we end up reading out the shadow of that event. So we've got a false reading now in frame N+1. Or we can happen to read out the peak hold signal just as the signal is peaking. And this is very difficult to be able to identify. And most likely in these scenarios, we've got the false reading in both frames. So we've got these different scenarios, and then we can keep or remove the data based on that. So you can see that by following these rules, we can remove a continuum of data which are caused by false events by not reading out the fully formed signal, and we can recover true events, which is the spectrum in blue, so that americium spectrum, which we're expecting to see. So that's another correction that we apply to the data to make sure we get the best performance. In detectors, there's quite often talk of pileup, and a classical pileup occurs when you have two events occurring very close together in time. So this, in our case, this would be when we have two photons occurring within the same shaping time. And when that happens, you'd see some strange effects in the spectra. So if you've got an input spectra like this cartoon of a bremstralum here, if you had too high a flux on your detector, then you start to get effects where you start to get this classical pileup, where you're starting to see higher energy events than the voltage of the X-ray tube, and you see an abrupt end of the spectrum here. And in HEXITEC, because each pixel saturates at a slightly different voltage, if you see a peak at around 180 to 200 kV, the likelihood is that you're saturating your detector rather than it being a real peak. And that, again, is just a warning. So to get classical pileup of having two events giving you the sum of the energies, then that would only ever really occur in a pulse source, so in a laser-driven radiation or a FEL. So that's really quite uncommon to happen. But you can also end up having effects similar to this, but at lower rates again. So there's some of the artifacts that we can see in HEXITEC, which are associated with the flux on the detector. If we have more than one event in a frame, then peak hold will always measure the highest energy event in that frame. So if you have too much flux on your detector, then what you're likely to do is to start to bias the spectrum that you're reading to look at the higher energies. So here we've got a case where we've got 3 events in a frame, and the peak hold is going to track that highest event and read out the highest energy. So when you've got an input spectrum like this one on the bottom, then your measured spectrum is going to be skewed, so you're measuring these high energy events rather than the low energy ones. So if you're seeing this type of data in there, you've probably got too many photons on the detector. but we also get effects at even slightly lower rates, which is why the occupancy is so important. So I mentioned before with the charge sharing, so when we've got our little array of pixels here with X-ray events across them, at low energy, if we have a monochromatic input, then we'll get this nice peak, single peak as an input. The spectrum that we'll see from raw data is this continuum from charge sharing, some X-ray fluorescence peaks, and then the peak at the correct energy. When we do the charge sharing discrimination, we get no continuum, we get the nice peaks. And when we do the charge sharing addition, we get the full peak height recovered, with some slight broadening because of the charge lost. If we get to higher occupancies, so if we throw in more X-rays into our frame now, then it gets ever increasingly difficult to be able to do the charge sharing corrections. So when we now go to do the charge sharing discrimination, we're starting then to see individual photons in neighboring pixels, and we'll throw these away even though they were separate events. We've got no way of knowing if they were charge sharing or separate photons. So as we do that, that means that our charge sharing discrimination data, even though we're at a too high a flux, we'd actually get no data from that. So with charge sharing discrimination, if you do see that your flux is going down when you're turning the wick up on your source, then you're probably in a scenario where the charge sharing discrimination is artificially throwing away events. When we go back to look at the data and do charge sharing addition, we can get a kind of pile-up effect as well. So in this case, we start to add up separate photons into individual pixels, and that will cause a skew in our spectrum for charge sharing addition as well. So if you have too many events, this can also skew the charge sharing addition spectrum. This is kind of what you can see here with this, what we call the neighbor pileup here, where you're starting to see that spectrum repeating itself in the higher energies. To calibrate the detector, we typically use an americium source, or maybe with a cobalt 57 source if there's higher energy applications as well. We do this on a per pixel basis. So we find the peak positions of these 4 peaks from the spectrum. We do a linear fit, and then that linear fit gives us a gradient and intercept, which we apply to the data, and also a low energy threshold per pixel. So when we look at that as an image, you see that we typically have around 29 EV per ADU as a conversion factor, and we have an intercept of around 1.5 keV. And you can see in here, you can see the structure of those 20 by 80 blocks in the raw data. And that's just because each of those blocks is going for a different readout chain. And then the intercepts are here, and then this is just showing the correctness of fit here. Those calibration values would be supplied with the detector, so it's not something that you'd need to worry about, but something that's relatively easy for people to recalibrate in situ as well. The thresholds, we typically set that in ADU, so that's set to 50 ADU as standard, and that allows us then to remove any noise below that level. So that's typically a value of 3 keV. You can start to see in the raw data that you have noise typically seen as across all of the rows. So this is a time-wise noise that you'll see, which typically comes from noise on the power supplies going into the ASIC. If you really wanted to, you might be able to track that noise and try and push that values down lower. It's something that we've done once or twice before in the lab, but isn't done as standard. I think we've got down to about 2.3 keV, I think is the lowest we've ever measured. But it wasn't easy. And the other thing that I mentioned really is that all these corrections and all these algorithms, they're stuff that we've written in STFC and other colleagues have written, and collaborators. All of our stuff is on a GitHub, which I think at the moment might still be set to a private repository, but it's there as MATLAB Python code, and we'd be happy to share that to people. So if that's something that's useful to people, then that's something where you can get in touch with quantum detectors, and we can start to open this and GitHub up for people to share things. And we're very happy and very interested to see people sharing what they're doing and how they're analyzing the data. There's probably lots of algorithms out there that we haven't thought of, so the more people doing it, the better for everybody. And something that we've always talked about doing, but never done as well, is that we'd also like to try and build on this collaboration and try and get some more workshops going. So I'm going to show some applications of people working and doing different applications of HEXITEC. But I'm probably not the best person to do it. It'd be a lot better if we had the people actually doing the science, giving these talks as well, and sharing what they're doing and their findings. So that might be something, if people have an interest in, something we might try and get going in the future as well. So I think one of the things of lockdown and having all these Zoom calls is actually realize it's not too difficult to get people together to share this type of information and have these talks. So hopefully in the not too distant future, I'll be listening to other people giving talks on Zoom as well. So to go on to some example applications. So the first example is from Manchester University. It's transmission imaging. So what you have is a source and then a sample and then HEXITEC sat behind it. And what you're doing here is you're measuring the spectrum per pixel, and that transmission spectrum has a lot of information in it. So using this spectral information, you can start to pick out different information about the material. So in this case, there's a K-edge, so there's an absorption edge in the material, which gives you a unique identifier for the elements in the sample. And then you can also use the relative intensities in different windows to estimate the absorption coefficients of the different materials as well, to gain contrast or material identification in there. In this case, they applied it to some example cases and a ore sample, so they could pick out the lead and the gold in this ore sample, but also the different types of stone structure in here as well, so different crystal types in there as well. And again, with this transmission imaging, typically you have quite a high flux, so that's something to be careful with HEXITEC, is that you're not going to have some of these occupancy effects that we talked about earlier. But if you set up the experiment correctly, you get some very nice and interesting data from this technique. The second one is an X-ray fluorescence technique. So this was done by Oxford University in collaboration with ESRF and Soleil synchrotrons. So in this case, we have HEXITEC to the side. We have a sample here in a furnace, and we're doing transmission imaging with a normal black and white radiography imager with a high resolution image. And then HEXITEC has got a pinhole to project an image of the X-ray fluorescence in the sample. And what Oxford University were interested in was trying to measure the elemental distribution in the alloy as it was solidifying. So in the furnace here, they've melted the alloy and then they're cooling it down to form the crystal structures in there. And you can see in the radiographic image, they can get very clean, sharp images of these structures being formed, but they don't really know what they are. But with HEXITEC, they're starting to get elemental information, so they can see the platinum and erbium in this case in the material, where it is in the melt phase as well, and that informs them how these crystals are going to grow. So it's quite a challenging but really interesting technique to give you this unique elemental information to your images, and fusing them with the high resolution and transmission images is quite a powerful technique. You don't need a synchrotron to do this though. You can also do this in the lab. So again, some work from Manchester using a very similar setup, and just using an X-ray tube with the HEXITEC at 90 degrees, and you can start to then get a spectrum per pixel, and then you've got these different elements here shown in different colors. And then for the test sample, they've shown that they can pick out these with these different samples. And that then can be applied for materials inspection or material science. And this is just a USB dongle, and they can pick out all of the higher Z elements in here that are typically in the capacitors here. So in these cases, this has been done with a pinhole projection, but similarly, you could do it with a collimator per pixel to increase the flux, or even with coded apertures as well. So I think there's quite an interesting technique to try and increase the flux of these type of X-ray fluorescence applications. HEXITEC can also be used not as an imager, but for having a multi-channel spectrometer, essentially. So this gives you essentially a high rate spectrometer, but it's also quite powerful for pulse systems, because you can get a value of the energy per pixel, and you can create a spectrum per frame rather than a spectrum per pixel. So you get a time resolving measurement of the change in the spectrum. And this was done by some collaborators at the University of Nebraska, where they're developing laser-driven radiation sources. So HEXITEC is the detector here, and then they've got a laser-driven source here with a gas jets, where the gas is then being turned into a plasma. That plasma is then being accelerated by the laser itself, and that acceleration is then giving off different types of radiation. They used HEXITEC to be able to measure the spectrum that's being emitted here from a pulse that lasted a few femtoseconds. But it could also be used as a technique for different time resolved applications as well. So using HEXITEC as a point spectrometer with many channels, is quite an interesting idea to be looked at as well. Another technique is X-ray diffraction. So this is something that we've conducted with diamond. So the I-12 beam line at diamond. Here we have HEXITEC set up at 5 degrees, using a pinhole again to project an image from the sample onto the detector. But in this case, instead of looking at the X-ray fluorescence, we're actually looking at the diffraction. So each pixel of HEXITEC is giving you an energy dispersive diffraction pattern. And they can be combined in different ways to give you information. And in this example, we looked at the battery. So with a transmission image here, looking at the battery, so a very similar setup before with the transmission image. Then HEXITEC was looking at the diffraction pattern, giving you chemical information. And you could see as the battery was charging or discharging, that these spectral features, these chemical features were changing in the battery. And we could match up these changes in the chemistry to the changes in the physical properties of the battery again, and give some insight into what's happening to a battery in an in situ situation. And again, it isn't just a synchrotron technique. So this is a diffraction technique that's been conducted at UCL mainly. So here they're using collimators on a conventional X-ray source to give a point source on a sample. Then HEXITEC is positioned off axis, and that point then gives you the diffraction pattern at different angles across the detector. So you get different energies, you'll get rings at different positions from the sample. And you can combine the energy dispersive diffraction pattern on each pixel to get you a single spectrum. And you can solve these materials at the order of around about a second using this technique. And they've shown that they can use it for a host of different applications. So looking at explosives in this case, so looking at these types of Semtex and C4, also to detect narcotics, control pharmaceutical processes, look at different types of tissue. So whether you've got cancerous tissue, fatty tissue, different food quality, looking at catalysts and battery technology as well. So it's quite a powerful technique. And if you can do that in the laboratory, that's a very useful application to do as well. And the final application that I'll mention is a relatively new development. So we haven't published any data on this yet, but we will be soon. So we've been working with Gunma University in Springate. So they pioneered a technique where they have a synchrotron source, high energy, being illuminating a battery. And they position, in their case, to begin with, they had a high purity germanium detector, which is positioned at 90 degrees to the sample. And the amount of scattering coming from the sample depends on the amount of electrons in the battery. So from measuring that electron count rate, they can essentially measure what's happening inside the battery. And recently, we demonstrated that we could do this with HEXITEC again. So instead of measuring a point source in the battery with the germanium detector, we can use a pinhole and take an image of that Compton scattering signal. And again, the intensity of the signal is telling you the amount of electrons in the sample. So this is a cut through here. So having a letterbox beam, you can image slices through the battery at different depths, and you can look at the density of charge in these different layers. So in this current collector here in the sample. And this is a sort of a new technique that we'll be publishing on soon. Again, a very interesting and novel way of trying to use that energy information of HEXITEC. So what is it that you can actually get and use at the moment? So quantum detectors have these units that we explained before. They'll operate in the energy range from about 3 to 4 kV up to around 180 or 200 kV. The energy resolution will be 1 kV at 1 kV full width half maximum at 60 kV. It'll operate at 5 kilohertz frame rate continuously, and will sit there collecting data until your computer is full. If we try and keep to an occupancy of sort of 10%, then this is a few million photons per second across the detector array. And as we saw before, it's with the 1mm CAD tail, which will be installed and biased and handled with the bias flushing all automatically. It's a plug and play system. There's demo systems available. So I think some of them are being dotted around the world at the moment. But if you've got interest in trying out HEXITEC, then I would encourage you to contact Quantum Detectors. If you just go on their website or Google HEXITEC, I think they're the first hit on there as well now. So if you get in touch with them, they'll be very happy to help you out and see what can be done to help your applications. I'd also add that customizations are possible. So in STFC, we always like to keep on pushing things, but also quantum detectors have these capabilities as well. So if you have any need for different geometries or being able to integrate the detectors in different ways, then do speak to quantum detectors as well. The single module system from the previous slide is still the easiest way to get going and the best way to test out ideas. So I'd suggest you do that first and then look at possibilities as well. So we can go beyond the single module system, but it all depends on what you need. So please do speak to quantum detectors if you have any questions or queries about that. And then all it remains just for me to summarize that HEXITEC is a spectroscopic imaging detector. It's got very good energy resolution from each pixel on an 80 by 80 array on a 250 micron pitch. Quantum detectors have taken the technology from STFC and they've improved its usability and its ability to use as a plug and play system. There's lots of different applications that have been used for HEXITEC already. And there's probably many more that we haven't thought of. Hopefully this is the start of more people using HEXITEC and we can start to build a user community around it as well. I would be very interested to see what people are doing, and I'm sure quantum detectors would as well. So if you do have any requirements, and do get in touch with quantum detectors, and I'm sure they'll be very happy to talk to you.